Okay, with that, let me talk a little bit about the midterm exam that you have next week. So that will start at, class starts at 6:45. It'll go for an hour and a half. And then we'll take a break after the midterm is over. And then we will have lecture, and I apologize that we have lecture after the midterm. That's never fun, but we've got a lot to cover in the class, so we will have lecture. If you finish the midterm early, you can excuse yourself, eat a sandwich or something, and then come back. I would say at 8:30, 8:30 something. Okay, maybe 8:40. It's written for 90 minutes. It's going to be all multiple choice, about 35 questions-ish, something around there. You are allowed a note sheet, one letter-sized piece of paper, writing on one side only. Be sure you bring your calculator and reference tables. I won't have any spare calculators. I might have a reference table, but don't count on that. Okay, make sure you bring your own reference tables. What else? I will provide Scantron forms for you guys. Give me a week to grade the midterm. Once I have the midterms graded, I will send you a grade report showing how you did on the exam and all of your other grades. Just kind of give you a progress report of where you are in the class. It will cover everything up to the stuff we covered today. Okay, so today we're covering some more on confidence intervals and things of that nature. And it will cover up to that. Okay. Are there any questions? Yes?
Will there be any practice midterms available?
I don't have a practice midterm, but on the web page there is there's a page that says about the midterm, and I list off a bunch of topics that you should know, and maybe some problems from the book that I think are relevant, but beyond that I don't have much. Okay, and that should cover like 95% of what you need to know. Yes.
So if we have done the homework, it's not going to be anything outside the scope of homework problems, are they?
I would say nothing outside of the scope of what's been assigned to you. Okay. So there might be like one question from R. Okay. Okay. All right. It's a fair exam. Well, of course I would think that, but it is. I mean, I think my quizzes have been fair, and the exam as well. Yes.
So the RCO questions will be like limited to the same kind of thing, like no making your own.
Yeah, right. I'm not going to have you write a bunch of code by hand to simulate a program or something. It'll be straightforward questions. Okay. We shall continue on in our studies. We might finish a little early. Well, I shouldn't say that in case we don't. Alright, so last week we talked about confidence intervals. discussion of confidence intervals today. So a confidence interval, the purpose of a confidence interval is to estimate or come up with a range for the values of mu, okay, or the value of mu, which is the mean of the population. So we want estimated mu, the mean of the population. We observe a sample. We take observe a sample. Okay. We assume that our sample was selected randomly, and each item in the sample is independent of the other items. Okay. So we assume sample. Selection. Okay, that's an important assumption, because if that assumption is not true, then the methods that we use to create a confidence interval are not valid. Okay, so the way we create a confidence interval is based off of the central limit theorem, and the central limit theorem depends on the idea that our sample is selected randomly. Okay, so we take and observe a sample. From our sample, we have a y bar or an x bar, the sample mean. Okay. And y bar serves as our best guess or estimate of mu. But we also know that it's very unlikely for y bar to be exactly equal to mu, so we create a small range or small interval of plausible values of mu. And the width of that interval depends on how confident we want to be. It depends on the amount of variation that exists within our sample, and it depends on how big our sample is. want to be more confident, our interval will have to be larger. If we're okay with being less confident, we can have a smaller interval. If there's lots of variation that exists in our sample, our interval is going to be wider. If there's very little variation that exists, our interval will be smaller. And if our sample is large, then we can have a smaller confidence interval. But if our sample is small, our confidence interval will be larger. And so all of this combines so that our confidence interval for mu is y bar plus or minus t star times s over the square root of n. The margin of error is everything that comes after the plus or minus. So this is essentially, the plus or minus part. So the margin of error would be t star times s over the square root of n. And s over the square root of n, that thing is our standard error. Okay, so we just have a few extra terms to throw around. The margin of error and the standard error. Okay? I'm hoping this all sounds familiar or we understand what's going on here from last week's discussion. Last week I also said it's important that when we talk about the confidence interval, we say I am 95% confident or I'm 90% confident, whatever confidence level we've selected, we say I am that much confident that mu is between here and here. And I said it's not correct for us to say there is this much probability that mu is between here and here. Okay? And we said it's not correct to talk about probability because probability is only makes sense for events of uncertainty. As for the location of mu, there's no actual uncertainty. The location of mu is fixed. The value of the mean of the population is set at some value, and so there's no uncertainty about it. The only thing that's uncertain is our knowledge, which depends on our sample, and so we can only talk about confidence, not whether or not mu is in our interval, because it either is or it isn't. There's no actual probability there. Okay. So we're going to expand on this, and we're going to use confidence intervals to compare the means from potentially two populations based on two samples. Okay. So comparing means from two populations. So what if someone wanted to know if there is a difference between the mean IQ of men and the mean IQ of women? Okay. Difference between this is referring to the population, mean IQ of men and the population. is there a difference between the mean IQ of men and the mean IQ of women in the population? Okay. Well, we can take two samples. So we have a sample of men and a sample of women. Let's say we have 15 men in our sample and 20 women in our sample. So to distinguish between the n that corresponds to the men and the n that corresponds to the women, I'm just going to put subscripts on them, n1 and n2. I could choose n sub m and n sub w if I wanted to, but I just arbitrarily labeled one group 1 and the other group 2. Okay, and let's say the mean of group 1 surveyed 15 random men. The mean IQ, let's say, was 98.7. So that is y bar 1. Let's say y bar 2, 100.4. Let's say the standard deviation was 15.1, and the standard deviation for group 2 was 14.8. Okay. So based on our samples, can we say that there is a difference between the mean IQ of men and the mean IQ of women? Okay. Well, if I only showed you the mean values of our samples, we would say the mean values are different, but they're not very, very different. They're only a couple points different. And so we're not sure, okay? Seeing that there is a good amount of variation within each sample, then that gives us further reason to believe that maybe there isn't a difference between the true mean value of men's IQs and women's IQ, okay? So at this point, maybe we would say the sample means are different, but not by much. Okay, and there's also seems to be a fair amount of spread in our data. So maybe we're not ready to say there is or is not a difference, okay, between the mean IQ of men and the mean IQ of women. Okay. So here's an example where the values are fairly small, the difference between them. Okay. What about so we'll keep that in mind, and we'll come back to that problem later. Here's another example. Okay, so you have maybe a group of athletes, okay, and we have soccer players and baseball players, okay? And we ask is there a difference in the running speed? So let's say we ask soccer players to run 200 meters, and we ask baseball players to run 200 meters. And we want to know, is there a difference between how fast the different athletes can run? Okay. Okay, so let's say so again, somehow we have to assume that our players have been selected randomly, or this is a representative sample. Maybe we're looking at, I don't know, Major League Soccer players and Major League Baseball players. Okay, so they're both from their respective professional divisions, okay? And so let's say we get a sample of 20 soccer players and let's say 20 baseball players. And let's say, I'm totally making up numbers, so I have no idea what would be a reasonable run time for 200 meters. Let's say 29.2 seconds and 33.4 seconds. I don't know.
That's pretty close.
Huh?
That's pretty close.
Does that sound reasonable? I'm just making up numbers here. Okay, and then I'm going to pick my spread numbers in such a way that this will be a decent example. So give me a second here. Okay, so let's say our spread here is 5.7, and our spread here is 5.5. Okay. What do we think? Is there evidence that there is a difference or is not a difference between the mean run times? Okay, well, how do you suppose we should answer this? I hope my numbers are good. Okay, so one, if I ask, does this provide evidence that maybe soccer players can run 200 meters faster than baseball players? Maybe, maybe not. Or maybe I should say, does this not that soccer players run faster than baseball players? Because that's actually a different question. I should ask, is there a difference between the mean running time of soccer players and the mean running time of baseball players when it comes to running 200 meters?
Yes.
So let's talk about what, so if we're asking about, what is the mean of the population running time for soccer players what is the mean running time for baseball players? And is there a difference? Okay. So, for the first two questions, I'm going to ask you to make a 95% confidence interval for mu for the soccer players and mu for the baseball players. So, make, for both of these, make a 95% confidence interval. So go ahead and take a minute to do that. Okay, so for soccer, I'm getting 29.2 plus or minus 2.67. So that gives me 31.87. And 6.53. Is that right? And over here I have 33.4 plus or minus 2.57. So that gives me 30.83 to 35.97. So what we got? Okay, so is there a difference between the mean running time for soccer players and the mean running time for baseball players? Maybe. Maybe not. Okay. All right. So these confidence intervals are valid for finding a value of mu. Okay, so when you look at one variable at a time, this is how we would make these confidence intervals. But this question of is there a difference is asking something else entirely. And we don't want to just say, look, I'm 95% confident that the mean running time for soccer players is between 26.5 to 31.87, okay, or 31.9 seconds. And over here, I'm 95% confident that it's between 30.8 and basically 36 seconds. And then we might be tempted to say, well, there's some overlap between the two groups, so it's possible that they have the same mean running time. Okay? It is possible that they have the same mean running time, but for that to actually happen, for the soccer players and baseball players to have the same mean running time for running 200 meters, that would mean our sample had to be on the quote unusual side for the soccer players in that we got a sample where our sample mean was lower than the true mean. And then the baseball players, our sample would have to have been a sample where the baseball players happened to be much higher, or not much higher, but just higher than the true mean value of baseball player runners. Okay, that's the only way that could happen for our data to show up like this. The only way it's possible for baseball players and soccer players to have the same mean running time and for us to see data like this is that our sample had to be low for the soccer players and our sample had to be high for the baseball players. Okay, and we would not see data like this if both samples were too low or both samples were too high, or if the other way happened where the soccer players happen to be high and the baseball players happen to be low. Okay, so in terms of the quote arrangements for whether our sample ended up giving us a number that was too low or too high, there's only one out of those four arrangements where we would see data like this. Does that kind of make sense? Okay, and so for us to look at intervals like this and to say there's some overlap, so we're not sure if we can't be confident about there being a difference, would also require that that extra, I guess, bit of unlikelihood had to have happened. Okay, so we can actually take that into account and develop an interval for just the difference using basically a smaller standard error. So rather than saying there's some overlap, soccer players could have a mean running time of 31 seconds and baseball players could have a mean running time of 31 seconds. Rather than saying, counting out something like that, we can just create an interval for the difference itself. Okay? So over here we made an interval for the mu of soccer players and the mu of baseball players. In this step, we're going to make an interval mu1 minus mu2. So this is the interval for the difference between means. And so, just keep in mind, this is the interval for the difference between means. So reasonable values for the difference between mu1 and mu2 will be values such as I'm 95% confident that the difference between the mean running time for baseball players and the mean running time for soccer players is between half a second and 3 seconds, or half a second and 4 seconds for the difference. Or I guess actually, looking at our data, it would be reasonable to say it's between 2 seconds and 10 seconds, or something like that. So we're looking at the difference between the mean running time. Okay. So our estimate for the difference between the mean running time would be y bar 1 minus y bar 2. So this would serve as our estimate. So we would have 29.2 minus 33.4, getting a difference of negative 4.2 seconds. And then, as for the standard error, we're going to combine the variance of the soccer players and the baseball players. Okay, so not the standard deviations directly, but the combine the variance. Okay, so the variance for the soccer players would be S1 squared over N1, okay? Because the standard error is S over the square root of N, right? And the variance, or I guess the variance of the error would be S1 squared over N1. And then I would also do that with the baseball players. But then to turn it back into a standard error, I would take the square root of these. So after I've combined the variances, to turn it back into a standard deviation or a standard error, I'm going to take the square root. Yes?
How come, and this is just a basic question, how come we did 29.2 minus 33.4? Is it just the wording of the question? Why not put 33.4 minus 29.2?
That's arbitrary.
It doesn't really matter.
It doesn't really matter. I did it because I wrote the soccer players on the left and the baseball players on the right. That's why I chose to do it that way. But the choice of whether to do 29.2 minus 33.4 or vice versa, 33.4 minus 29.2 is arbitrary and doesn't really matter. Okay.
Because you're going to square it anyways?
We're not going to square it, but I'll tell you the difference at the end of this, okay? I think you'll see that it doesn't matter. And I'll explain in a minute. So, okay, so I've done 29.2 minus 33.4. I get that as my estimate for the difference between the means. And then we've got this value for our standard error. Okay? And so just plugging in values, I get 5.7 squared over 20 plus 5.5 squared over 20. And I take the square root of this, and I get some other number. I get 1.771. It's a good idea to just make sure when you punch this into the calculator, you also get 1.771. Because if you don't, then you might have some problems. So the only thing that's left is figuring out what to use for our t star as our confidence interval. Okay. So The selection of T-star depends on our degrees of freedom. So the truth is, the degrees of freedom, when you have two independent samples, the degrees of freedom is actually complicated to calculate. Okay, it's actually, there's a complex formula for finding the degrees of freedom. And so, it's okay when you are using a computer. You can have the computer calculate the degrees of freedom for you rather easily. But when you are doing things by hand, you probably don't want to mess with the true degrees of freedom. I mean, you could, but it would be rather tedious. So we have approximations for the degrees of freedom. And we have, I guess, the generous or the miserly or conservative side of the approximation. So the degrees of freedom will generally almost always be between n1 plus n2 minus 2. This is on the quote generous side. And then n minus 1 using the smaller of n1 and n2. So the degrees of freedom will usually be between these two numbers. And I guess depending on who you ask, should we use the larger number of degrees of freedom or the fewer amounts of degrees of freedom? If you want to be on the safe side, use the fewer, smaller amount. Okay. But for most purposes, unless we're talking about something very critical, this will probably give you numbers closer to the reality. Okay. So for our class, we will use n1 plus n2 minus 2. But if you ever take another statistics class, they might tell you to use this, or they might tell you to use something else. Okay, so we will use so in our case, so in this example, degrees of freedom will be 20 plus 20 minus 2. We have 38 degrees of freedom. Okay. And then when you go to the table and you look for 38 degrees of freedom, you do not find a listing for 38 degrees of freedom. Okay. Again, these are only problems that we experience when we are dealing with, when we're doing calculations by hand and using a table. Okay. If you had a more detailed table, you might have a line for 38 degrees of freedom, and you would use that. If you're using a computer, it'll find the exact degrees of freedom for you and use its own built-in table. These are just problems we experience when we're doing calculations by hand and using a table. We don't see 38 degrees of freedom, so to stay on the safe side here, always round down. Okay. So in the table, we will select 30 degrees of freedom. Okay, so we're rounding down. There's 40 degrees of freedom in the table and 30 degrees of freedom. Because we're using the kind of the generous number, we're figuring out our original degrees of freedom anyway. We're going to play it safe and always round down. Yes?
Do you ever term more than two things, like two populations, and then with like the degree of freedom would be like n1 plus n2?
Okay, so you could not do a confidence interval for more than two populations, okay? You would have to, because you can't have a difference between three items. If I said, I have a child who is 5 years old and another child who's 7 years old and another child who's 12 years old, what's the difference in ages? You can't answer that question. You can only say Well, the difference between the oldest and the youngest is this many years, or the oldest and the middle is this many, or the middle and the youngest is this many. But if I just said, what's the difference in ages, and I give you 3 numbers, that we don't have a term for difference then with 3. So when we're talking about confidence interval for a difference, we can only do it with 2. Okay? We'll learn later on in the course how to deal with multiple populations. But for now, just 2. Okay, so using 30 degrees of freedom, 95% confidence, what is the number that we're going to use? 2.042.